we're talking about logarithms, about natural logarithms, about rules about logarithms, how to transfer from logarithmic form into exponential form and back again. What does it mean when I add, subtract, multiply, divide, logarithms, all that sort of thing. Take powers, bring it out front. We talked about all those rules yesterday. So let's pick it up where we left off. Express as a single logarithm. We did this many, many times in algebra 2. Way back when. Those were the good old days. Express ln of a plus 1/2 ln b as a single logarithm. I remember doing a lot of these where it was like no calculator, express as a single logarithm, and then simplify, things like that. Speaking of no calculator, I was just looking through your test for next week. So basically what's going to happen is tomorrow I'm going to give you your take-home quiz. When you come back on Tuesday, because we got 4-day weekend, when you come back on Tuesday, I am going to give you, because we only have sections 1-1 to 1-5, that's it for chapter 1. So when you come back on Tuesday, I am going to give you the test review. And while you're working on that, I will grade all of the take-home quizzes and get them back to you by the end of the period. I'll input them and everything, because it's only 12 weeks, so it's pretty easy. So I'll give them back to you by the end of the period. And then on Wednesday, we'll go over the test review as well as any questions that you had on the take-home quiz. And then our test, which is really not actually a 2-day test, it's probably like a 1.5-day test, I'll give you over the course of Thursday and Friday of next week. Okay? So it's 2-day test next week. But again, it's not like a 2-hour test. It's not like an 1.5-hour test. It's like probably like an hour test, maybe an hour and 10-minute test. Many of you will finish early. But again, I have to give you a good chunk of time like that because, again, this is a college class. I like to think of it this way. A college class would normally be an hour long, and they would give you the entire hour to work on the test. So I am going to give you guys at least an hour to work on the test. So that means like a period and a half or 2 periods left. So speaking of that, since it is 2 days, one of the days is going to be no calculator, and one of the days is going to be calculator. And I'll, on Tuesday of next week when I go through I guess I should say, yeah, that's right. On Tuesday of next week when I give you the the test review, I will tell you, okay, question this to this, you should be doing without a calculator. All right, back to this. Express as a single logarithm and then simplify. Or really just express as a single logarithm. So what does this power do? I said it. Oh, shoot. What does that 1/2 do? What does that 1/2 become? It becomes a power, right? It moves back on top of the b. Remember, the rule is for any logarithm, if you've got a number multiplied out front, you can put it on top of the of number, right? This is ln of b. You can put it on top of that as an exponent. So next step would be to say, okay, ln of a plus ln of b to the 1/2 power. ln of a plus ln of b to the 1/2. All right. So now I can say addition means to what? It means to multiply. So this means I can take ln of a times b to the 1/2 power. And the only other thing that I would do is I don't like to leave fraction powers. I guess this would be okay. But this, to me, is a little bit more simplified. ln of a times square root of b. And I'll put that in parentheses for good measure. Don't really need the parentheses there, but you might be tempted to say it would just be ln of a, dramatic pause, times the square root of b. Okay, questions about that one? Right there? All right. The following formula shows that logarithms with any base can be expressed in terms of the natural logarithm, or any base. Or any base. You could transfer any base of a logarithm into anything you want. Now, this isn't as useful as it has been. This isn't as useful as it was a long time ago, because your calculators do pretty much any logarithm base. Does anyone have a calculator that looks like one of these old school ones? Does anybody have one of those? Or are they all like the color editions, right? The newer ones. If you've got an older one like this does not change the base for you. Like my calculator in my screen, if I go to math, and I think it's in here, and I scroll down, there's no log base function. Yeah, I just skipped to the top of the list. There's no log base function, where if you guys hit math in your calculator, it shows you a log base function where you can go in and input the base of the log, input the of number, and it solves it for you. I can't do that. I can't perform the log of any number. What your calculator is actually doing for you is changing the base into something that it can do. See, my calculator right now, as it stands, will only calculate ln, natural log, or what is the log base there? Log base 10, right, log base 10. If it's not written, you assume it's log base 10. So my calculator will only do natural log and log base 10. So a way around that is by using this change of base formula. It says that no matter what base or of number you have, you can change the base and you can change that log base into anything you want. For example, natural logarithm. You can make anything a log base e. So say you had log base b to the log base b of x. You could say natural log of x divided by natural log of b. Natural log of x divided by natural log of b. You could make that into anything that you wanted. Like you could say, I'll write it up here so we can all see it. If you had log base 3 of 4, you can't compute that mentally. 3 to the what power is 4? That doesn't make sense. It's 1 point something, right? But what you can do is say natural log of 4 divided by natural log of 3, if that assists you in any way. Now me, I'd still have to go back to my calculator and do that way, but I can still do it as a natural log. Like you guys can go ahead and plug this into your calculator where I cannot. I would have to do this. I would have to perform the natural log. Something else I could do is turn it into common log base 10. Like if I wanted to do log base 3 of 4, I could change the base into log base 10. Log base 10 of 4 divided by log base 10 of 3. I think that's really cool. That's why I still teach it. That you can, that just seems weird that you could just like poof and make it anything that you want. Like what? What? Where? How? Why? There's the proof for it. If I say let y equals log base b of x, so if I have just any log base b of x, doesn't matter what it is, doesn't matter what base, doesn't matter what of number. If I change that into exponential form, b to the y is x. Okay, all I did was take this logarithmic form into exponential form. And then I perform the natural log to both sides, which is something that you can do. You can take the logarithm of both sides to solve an equation. I take the natural log on this side and the natural log on that side. That would get me ln of b to the y is equal to ln of x, right? Natural log of the left side and natural log of the right side. Presto changeo, bring this out front. I get y ln of b is equal to ln of x. Divide ln b over to the other side, and we have our change of base formula. I think that's really interesting, the fact that you can just make it any base that you want. Just pull it out of thin air. You want base 5, you make base 5. Doesn't matter. Scientific calculators have a key for natural logarithms, so that's why it's useful. And, it's funny that those calculators, those log-based calculators that you have right now that everybody has, that was not a thing until like 4 or 5 years ago. Like that's really new stuff. So this calc book, which is relatively new, doesn't even know that your calculator can do that. It still thinks that you can only do common log and natural log. So again, evaluate log base 8 of 5. So that means I would just take log of 5 over log of 8, which is actually equivalent to taking ln of 5 over ln of 8. Now, you guys, I want you guys to go verify that. I want you to plug in your calculator using your log base function. And if you don't know where it is, let me remind you. You hit the math button, and then you just keep scrolling until you see log base. Please let me know if you do not have that, because then it's going to be even, then it's going to be even more important that I show you the log base function. I can't show you on the screen because I can't. I don't have it. I just keep scrolling. So you plug it in, you plug in the base of 8, and you do your out 5, and you get it. For me, this is what I have to do. I have to do log of 5 divided by log of 8. And this is what I get. But it's interesting enough to point out that natural log of 5 divided by natural log of 8 is also the exact same thing. No matter what we change our base into, common log, natural log, you get the exact same thing. Okay. Can you scroll, please? There it goes. Yeah, thank you. The graphs of exponential functions, y is equal to e to the x and its inverse function, the natural logarithm function are shown. Figure 13, which is in book, sorry. What are we doing here? Oh, we're just graphing. Okay, graphing ln of x minus 2 minus 1. So let's graph a natural logarithm. Let's do it by sketching it using the transformations that we know. Okay. Now, thinking about my parent natural log. This is my parent natural log. I'll put it in green. Okay, this is our parent natural log. The asymptote is the y-axis. Okay, the natural log of x, the asymptote is the y-axis. So now let's perform the transformations on it. What are my transformations that I see? What are the two transformations that I see? Right 2, down 1. Right 2, down 1. Good, right 2, down 1. So I'm going to make this go right 2, down 1. So this what the asymptote was at the axis. So I'm just going to say, okay, right 2, the asymptote is now here. That's my new asymptote. So it's going to start here and then just go down 1, which shifting it down 1, you're not really going to see very much because it's just shifting like my x-intercept down 1 a little bit more. Okay. You can calculate the x-intercept rather easily if you needed to, and I think it asks you to. I'm going to shut the door. It's a little rowdy out there. Getting memory back. You can pretty easily calculate the x-intercept by just setting the y value as 0. So let's do that. 0 is equal to ln of x minus 2 minus 1. So it's going to be x comma 0, right? So set the y value equal to 0 and let's solve. Okay, add the 1 over to the other side. ln of x minus 2. Now, how do I keep solving? Once I'm stuck trying to evaluate a natural logarithm of x, what undoes a natural log? What undoes a logarithm? An exponent. So what I have to do is take it from logarithmic form into exponential form, right? This is log base e, so it's going to be e to the first power is equal to x minus 2, right? I could have rewritten this to look like this. 1 is equal to log base e of x minus 2. Right? Those two mean the same thing. And then I do my spiral. I say, okay, e to the first is that. And now I solve that equation just by adding 2 over to the other side. So the actual intercept is e plus 2. That's the exact version of it. So what is it here? E plus 2, 4.718, which seems about right. It seems like my sketch ended up in the pretty right spot. That was 2, 3, 4. Yeah, sure, 4.718. Okay. So you can find your x-intercept pretty easily if you're asked to, and you are asked to in some of the homework problems. Okay, so we talked about inverses of linear functions, rational functions, all sorts of functions, but the one inverse that we have not talked about yet is inverse of trig functions. Inverse of trig functions, inverse sine, inverse cosine, inverse tangent. Okay, when we try to find the inverse of a trig function, we have a slight difficulty. Looking at sine of x, is sine of x 1 to 1? Is sine of x 1 to 1? No, it does not pass the horizontal line test. So what we have to do to make it 1 to 1 is restrict the domain. we have to restrict the domain of sine. So what we're going to do is we're going to restrict it from negative pi over 2 to pi over 2. Remember the restrictions of the domain for the three trig functions? Both sine and tangent are negative pi over 2 to pi over 2. Cosine is 0 to pi, right? Those are the restricted values for sine and cosine, and I think they're on the next slide. Or sorry, sine, cosine, and tangent. But why do we restrict them? We restrict them so that they can be one-to-one, so that the inverse is also a function itself. Okay. If you ever see the notation arcsine, did Mr. Delap ever use arcsine? Maybe once or twice. That's not very commonly used. Arcsine is just saying inverse sine. It's just like the restricted value of inverse sine. Okay. All right, let's take a look here. Since the definition, yeah, inverse sine is pi over 2, negative pi over 2 to pi over 2. All right. Evaluate inverse sine of 1/2 and tangent of arcsine of 1/3. Okay. You could perform these operations by looking at your unit circle, but you could also perform these operations by figuring out or by using right triangles as well. Like in my mind, I look at this and I know 1/2. Isn't there a coordinate that has a 1/2 on it? Yes. So I'm going to use my unit circle. But jumping to B real quick, is there anywhere where you see a 1/3? No. No, there's not. So I'm going to have to do something a little different for part B than I am for part A. Okay, let's take a look at part A. Part A. No? Part A. Party? Okay. Part A. No? Next time. Yeah. Okay. Evaluate inverse sine of 1/2. Okay, so sine is x or y? Y value, right? So I'm looking for, along the unit circle, the coordinate has the y value of 1/2. Which one is that? Which one has the y value at 1/2? Now remember that if you're ever struggling with this, we'll just kind of sketch out your unit circle and say, okay, the 45 family is the one with the radical 2's. So it's not the 45 family. It's either the 30 family or the 60 family. It's either the 30 family or the 60 family. Okay, if it's the 30 family, this is 1, then my short side is the 1/2 and my long side is the radical 3 over 2, because that's the 1 to 2 relationship with the short side. If it's the 60 family, this is 1, the hypotenuse is always 1, then this side is the 1/2. Okay, so which one is it? Is it the 30 family or the 60 family? The 30 family. Right? It's the 30 family, which we know to be the what? In terms of pi, what would that be? Pi over 6, right? So we know that this is pi over 6. Now, for our purposes here, we're assuming that we're using the restricted sign. Okay? I'm not going to say pi over 6 plus 2 pi n, because I'm assuming that I'm going to use restricted sign. And especially when I use this terminology, that is also the restricted sign. It's like reinforcing the fact that don't forget it. It's only negative pi over 2 to pi over 2. Okay. But I said, so pi over 6 was my final answer and my only answer. Right? I know there's another spot along the unit circle that has that same y value, namely over there, but we're only talking about negative pi over 2 to pi over 2. Another way that we could have written that is done this, and that's what we introduced in Algebra 2 when we use capital S sign. That's another way to really reinforce the fact that we're only going to use the restricted values. Okay, so arcsine of 1/3. Arcsine of 1/3. Let's take a look here for part B. Arcsine of 1/3. What I'm saying here is if I have a triangle and I have my theta, because arcsine is going to be equal to a theta. I'm looking for my angle. And arcsine is equal to, or I'm finding arcsine of 1/3. So the sine of the angle is equal to 1/3. Well, sine is opposite over hypotenuse. Opposite over hypotenuse. You see that there? I can create my right triangle. by finding arcsine of 1/3. And I know that the angle theta here, I can find the other side length, 1 squared plus b. b squared is equal to 3 squared. So b squared plus 1 is equal to 9. So b squared is equal to 8. Or when we square root it, 2 radical 2. Put that, take that on the video. So we got 2 radical 2. Now, how does that help us? Okay, how does that help us? Well, once I know that my b value is radical 2 over 2, okay, not radical 2 over 2, excuse me, 2 radical 2. Thinking too much unit circle. All I want to do is find the tangent of that angle. See, look at the notation here. This is going to produce me the angle, but in the end, all I want to do is take that angle and find the tangent of it. So what is the tangent of theta here? Tangent of theta is equal to opposite over adjacent. You follow me there? So if you ever have an angle, or if you ever have a value that's outside of your unit circle, you can create the triangle and then use that triangle to help answer the question. Like, for example, here, I'm not ever really finding what radian measure this is. I don't really care, because all I'm doing is taking that angle and just finding the tangent of it. And if I've created my triangle, it's pretty easy to find the tangent. So just to rationalize here, I'm going to take this. So radical 2 over, and that would be 2 times 2, or just 4. Interestingly enough, you're going to find throughout the year that we're going to leave rationalizing the denominator kind of by the wayside. Because we're going to get into things that's very, very difficult. It would be extremely difficult to rationalize the denominator. So it's going to kind of, at some point in the year, it's going to kind of just go away. Yeah. All right, last question here. Cosine of inverse tangent of x. Cosine of inverse tangent of x. Same type of thing here. Can I find x in this case? Like if I can't really figure out what my angle measure is, right? But I know that inverse tangent of x is equal to some angle measure, to some theta, right? So I know that x is equal to tangent theta. I can create a triangle so that the tangent is x pretty easily. Take a look at our triangle here. So if this is theta, tangent is x. Well, tangent is opposite over adjacent. Opposite x. What would be my adjacent if my opposite is x? 1. Doesn't theta have a tangent of x? Opposite over adjacent, x over 1. Okay, so look at what I'm trying to find. This is going to get me my theta, right? Well, all I'm really trying to find is cosine theta. So my end goal is going to be to do adjacent over hypotenuse. So I just need to find the hypotenuse of this triangle. 1 squared plus x squared is equal to, let's call that c squared. Okay, so that's 1 plus x squared, the square root of 1 plus x squared. That's my c value. I don't have to do the whole plus or minus thing in front of the square root because the length cannot be negative. So this is the square root of 1 plus x squared. And now I can find my cosine. Now I can find the cosine. The cosine of theta is going to be, not opposite over hypotenuse, adjacent over hypotenuse, 1 over square root of 1 plus x squared. Adjacent over hypotenuse. You know what's funny? It's funny that I mentioned the whole not rationalizing the denominator thing, because you know what the book's correct answer is? That I'm leaving a square root in the denominator. We're going to find that it's kind of like I don't know. It's kind of understood that you would have to rationalize the denominator, and you don't have to do it algebraically. Okay. But totally is an acceptable answer. This would have been fine as well if you wanted to rationalize the denominator, because you would just multiply by the square root of 1 plus x squared to the top and the bottom. But I am completely fine if you do not rationalize the denominator from here on out. All right, let's stop the video, and I can let you go on your homework.